Now I start another subject, which is called atmospheric effect. So assume that we have this topography and this of the boundary, and the measurements at the surface of the Earth, and we have atmosphere above the gravity anomaly here. These are atmospheric masses. We write this here. Atmospheric masses. And as you see, the data that we have are under the atmospheric masses. Then, therefore, we should use the internal type of the potential for correcting the effect of atmosphere. But the problem is that the atmospheric effect, the atmosphere density, density is changing by height. So for the topography, we could assume that the topography doesn't change radially. For example, if we have topographic mass density here, the density here down at the boundary is the same with the density at the surface. It means that they are the same density. And the density can change laterally, but we assume that it's constant. But for the atmospheric effect, we cannot do so, because we all know that when at the surface, at sea level, the atmosphere is denser than at higher level. So how it is so? Then I will say that the density of atmosphere, based on the power model, there are also exponential models as well for that. But my professor suggested the power model. I have written a paper to prove that this is equivalent to the exponential model. And also I have another model that you can look at my PhD thesis I have done. So this is the atmospheric effect, the atmospheric density, atmosphere density at sea level. And this one is atmospheric density at any level. Atmospheric density at R inside the atmosphere. R is the radius of the Earth, and small r is the geocentric distance. So the only thing that which makes derivations different than the topographic effect is that the atmosphere cannot be assumed constant. It is changing radially. So how do we solve this atmospheric effect? Simply, again, we write Newton integral, and here the summation, and R from the surface of the Earth maybe to infinity, and the density rho 0, of course, over R, and this one will be all over R, and V nu is a constant. R prime, this should be also R prime, square dr square d sigma. So maybe let me call instead of infinity zeta, so it's much easier to assume it. If I do so, then we have g integral, double integral. Then I can write this integral in that form. I said, okay, from r up to z, rho 0 over r multiplied by r over r prime v r prime 2 dr sigma minus g integral, double integral of, then this time from r to r plus h prime. And again, rho 0 over L, r over r, mu r prime 2 dr prime. So you need to perform the radial integral. Thereafter, you need to perform expand the binomial term in Taylor expansion. And when you do so, you will simply come to an equation like this for the atmospheric potential. Atmospheric potential of internal type will be summation. I just write the result. Derivations are left to yourself to find it. To infinity r over r n summation n minus m to m v n m y n m theta n lambda. So this is the same equation for the internal type of the topography, but the spherical harmonics, the coefficients are not the same. And they are, you can write it here. For pi g r 2 rho 0 to n plus 1, and it will be the power model, exponential power density model. It will be z n with Kronecker delta minus spherical harmonics of the topography, and mr minus n plus v minus 1 divided by 2R2 Z2 delta N 0 minus H2 and that's the spherical harmonics. So as you see, atmospheric effect is always above the computation points here, always atmospheric effect computed like it. And when you want to compute the geoid, let me clean it. When you compute a geoid model, you will remove again the topography effect, but with a compensation. So the compensation I consider, or reduction, to make the size smaller, and thereafter I will remove the effect of the atmosphere from the gravity data. When I did that, I continue them downward. Then I come to this. Again, the same thing. Delta G T minus delta G compensation and delta GC and delta G. I can put the compensation on also, you do not come, but it is okay that if you do term by term down. You do downward continuation by one, it's okay. So then you come to cogeoid. By Stokes. And here you will add the corrections to the cogeoid, the corrections of the topography, and compensation, and you will add this. Add the topographic effect minus compensation minus atmospheric effect. Then if you add this to the big plus here, you come to the geoid. So it means that you need to continue downward the topographic effect, compensation, and atmospheric effect. From external type, you will come to the geoid level, do the computation as the geoid, and using the internal type, restore the effect of the removed masses. That's all. So consider that for atmospheric effect, you do not need any reduction because it is small. It is in the order of the gravity anomaly, maybe smaller. So you can simply just remove and restore it without any problem. You don't need to consider any reduction for that atmosphere. So why you have to restore it? Because when you remove it from it, you are changing the Earth system. You are changing the true gravity, the real gravity. And when you restore it, you restore it to bring back the Earth in the balance. So it's important to perform remove and restore.